Hello, I'll be doing a quick tour on how to create data transformation pipelines that run locally and are first and foremost fast, so we don't want to make any compromises on performance. Secondly, the goal of the API is to be as simple as possible, so we want the API to be easy to understand, easy to extend, but also easy to use, with a familiar feeling if you've used other streaming libraries. So this API is part of the Aux library. The goal of the Aux library is to provide you, the programmer, necessary tools to write code in direct style using a modern functional language, that is Scala, on the JVM. We are also relying on a very recent version of the JVM, Java 21, which includes support for virtual threads. And virtual threads are the way through which Aux achieves its performance goals while maintaining a programmer-friendly direct syntax. So we will be looking at the flow component of Aux. If you have used maybe Kotlin Flow before, it's a very similar construct. The Aux flow is actually inspired by Kotlin Flow in many areas. Other sources of inspiration include Akka Streams or FS2. So if you have used these APIs, this should look familiar. We have tried to remove some of the obstacles, some of the harder parts of those APIs in our approach. And as I mentioned, we also rely heavily on virtual threads. So we will look at a couple of examples to get a feel of how you can use Flow, and hopefully by the end you will feel encouraged to actually try this at home. Okay, so let's start. So let's first look at some very simple examples without any concurrency. The flow, a flow object, a flow instance, describes how the data that is emitted by the flow should be transformed, what kind of operations should be done. So when you create a flow, nothing will happen initially, so you will only create the description step by step, and when your description is ready, you can run the flow in various ways to actually make the data flow through the pipeline. So let's look at a very simple example of a finite flow. There's no concurrency here, this whole thing will run on a single thread without spawning any background threads, virtual threads, and so on and so on. So what we are doing here is we are creating a finite flow which will emit 8 values and then complete. As I mentioned, when we call flow.fromValues, we will only allocate some data on the heap. Nothing will actually get emitted, transformed, or anything. So then there are some familiar looking operations. So if you have used the Scala Collections API, or in fact any other streaming library in Kotlin, in Java, or in Scala, I think .map, .filter should be familiar. So these operations are there on the flow instances, and when you call .map, we obtain a new flow instance, which includes this additional mapping transformation step. Then we have some more operations that are not available in the standard library on collections. So we have some operations like intersperse, which inserts elements in between consecutively emitted values. We have map stateful, so that we can compute the running total of the values emitted over here, right? So that's our initial state. And when a new element, when a new value is emitted, we update the state with the running total, and we emit the state and store it for later usage, right? So this over here is a description of the flow. So eventually, when the description is done, we have to run the flow. One of the ways to run the flow is to collect all the values that it emits into a list. Of course, this makes sense only for finite flows. So we can run the flow into a list. That's what we are doing here. And finally, we are printing the results. So we are using the pipe helper function from Aux, which applies the result of the object on which it's called to the function is over here. So we print the result. We can run this and yeah, you can see that it emitted a couple of values, which is the incrementally computed running total that is the result of map stateful. Flows can also be infinite. So over here we create an infinite flow which will emit consecutive natural numbers. And then we can also, do some operations. So we only take numbers that are divisible by 3. To actually see something on screen and not hang the computer, we only take 5 elements, and then we use a different way to run the flow. So here, for each element that is emitted, we actually print it to the standard output. So we don't collect it to a list, but we print those elements as they come in. So we can run this. And you can see that, yeah, it kind of emitted. So these are the first 5 numbers that are divisible by 3, the first natural numbers. So this, I guess, kind of works as expected, nothing special here. What's important to note is that in a flow, the next element is only emitted once the previous element has been somehow consumed. So this flow over here will emit 0, so this will flow through the filter, the take, the print line, and then we'll go back to the beginning, and so on and so on. So we won't accumulate an infinite number of integers in memory or anything like that. Okay, so that's these are the very basics of a flow. So once again, a mix of an API that you might know from collections and some APIs that you know from the streaming libraries. But of course, it gets much more interesting when we introduce some concurrency into the mix, and that's actually where the most value of flow comes from. So let's look at how we can do some concurrency using Ox and Flow. So as a first example, let's say we have a flow which emits the letters A to Z in a loop forever, right? So that's, once again, it's an infinite flow. So here we create an infinite flow which emits ranges of A to Z, and then we flatten this flow. So each range emits all the elements in this range before proceeding to the next one. And then we also have a flow of numbers, right? And we might want to create a flow which contains pairs. So we want to number the element of this left flow, right? So we will obtain a flow of pairs where the first element of the pair comes from the first flow and the second from the second flow, right? So once again, of course, this will be an infinite flow. So what happens under the hood when we are doing .zip is that we are running both of these flows concurrently. That is all managed by Ox. So we are running those two concurrently. They emit their results to a channel. A channel is a lower level concurrent data structure, also inspired by a similar data structure in Kotlin. It's very efficient, it's fast, it supports completion, it supports error handling, it supports go-like selects, so that's also useful in some operators, as we will see later. So these two flows are run concurrently and they emit their values onto a channel, and then in the main thread, which actually runs the .zip operation, we are taking one element from the left channel, from the right channel, and combining them. And we can see that we should get the first 100 pairs, right? So if we go up over here, you can see that we've got A with the number 0, B1, and so on, and at some point this will loop over and we start from A again, right? So there are 26 letters in the alphabet as expected. So that's one way you can do concurrency. Another way is merging two flows, right? So that's actually in the implementation of merge, where the select operation is useful from the channels perspective. So here we have two flows. They emit values every 123 milliseconds and once every 312 milliseconds, so in irregular intervals. What merge does is it runs both of these into a channel, so these flows emit values onto a channel, and then merge on the main thread selects a value that is actually present on one of these two channels and emits it further down. So once again we can run this, and you will see more lefts than rights because left emits more frequently, once again as expected. What is important to note here is that this concurrency that happens here is actually hidden from you, and that's the best style of concurrency because you don't have to worry about it. There's error handling that's built in, so error handling is performed using structured concurrency. So inside of merge we open a structured concurrency scope. If you would like to read more about it, you can take a look at the documentation of Ox. It contains a section which is an introduction to structured concurrency. So yeah, there's a structured concurrency scope that is opened. Then we have two background threads that are started, which actually run the two flows. In case of any error, before merge completes and propagates the error to you, the concurrency scope will end, and this will cause any background threads to be interrupted, and we will wait for them to terminate. So it's guaranteed that there will be no leftovers in terms of any background threads still running if merge ends with an exception. So error handling is done nicely. Another very useful concurrent operator that you might know from, for example, Akka Streams or FS2 is doing a parallel map. So let's look at this example. So actually here we are also seeing how you can use the I/O capabilities of a flow. So there are a couple of built-in functions which allow you to read files, read input streams, manage chunks of bytes, and combine them into lines, for example, right? So here we are reading this resource. So it's a list of first names, of Polish first names. So this actually returns a flow of a chunk of byte. So you can see here it's a flow chunk byte, but then we combine these, we parse those lines, we parse those chunks into lines of text, assuming UTF-8 encoding, and then we just make them look nicer. So that's the base flow, and then what we do is we do a parallel map. So the body of this map will be executed at most will be executed in the background in background threads, and at most 4 of these background threads will run at a time. So mapPar preserves ordering, so if name A comes before name B in the flow, the result of the map will also be emitted in that order, even if the background processing of the second name completes before the first. There's also another variant called unordered, where the ordering is not preserved, so it might emit elements faster. Yeah, but here we guarantee that at most 4 elements will be processed in parallel concurrently. And as part of another interesting thing over here is that as part of processing the elements, we actually perform HTTP requests. So all of this is run, so all of these background threads that are created, they're actually virtual threads. So it's a light form version of a Java thread, which can be created very quickly, which is cheap in terms of memory. It's cheap in terms of context switching. And they're actually encouraged to create a lot of them, so it's not a problem. And what we do here is we send a blocking HTTP call to actually process this name in some way. So here we are connecting to a localhost server, and the server is defined over here. So the server definition uses Tapir and other of our libraries. That's not important. Important is what the server does. So it pretends to do some processing of the data it receives. So it sleeps for a random interval and then it just returns hello. So that's the processing. So we'll actually start this HTTP server in the background so that we can do some testing. Yeah, it started. Okay, we are going back to our client. So over here, each of these 4 background threads, that is at most 4 background threads that is started to process this data, will actually execute blocking calls. Since we are on JVM 21, since we are using virtual threads and Project Loom, doing synchronous blocking calls is completely fine, and is actually the way to do blocking, to do I/O in a block way. So we don't use futures, we don't use effect systems, we just do blocking calls, right? So the send over here will block and wait for the response. So actually we can run this. So we should see some, responses. So they come generally in pack of 4s in an incremental way. So each of these results is a result of invoking the server. Okay. So speaking of Loom, Loom tried to solve a couple of problems when it came to concurrent and effectful programming on the JVM. These all were problems that were introduced for some very good reasons, mainly to be able to scale backend Java applications so that they can handle a lot of requests per second, for example. Loom identified 3 of these problems. So they were lost control flow, meaning that you can't use native control flow operations inside of your code. If you're using futures, for example, or effect systems, you really have to use control flow operations which is provided by these data types, not like ifs, loops, whiles, fors, and so on. The second is that the stack traces that are thrown when using, for example, futures are usually not that useful because they don't contain the full context of the call. They usually just contain the portion of the stack trace from the last map, right? And finally, the third problem was that futures or effect systems are viral, meaning that if you have some piece of code that returns a future, if you want to call that code, you have to return a future as well. So in the end, your entire code base uses futures. So these are the 3 problems that Loom tries to solve, and Flow and Ox in general and Ox Flow in particular follows these. So let's see how these are fixed. So for example, here we have a variant of the previous demo. Once again, we have a mapPar, and over here we can do arbitrary control flow as part of the logic that actually transforms our data, right? So here we can say that if the name has a particular ending, we will actually try to create a feminine version of that name by adding a at the end. So it's a trick that works for some Polish names, not for all, but as far as I checked, it works always when the name ends with these particular letters, and otherwise we just skip it, right? And as I said, we can do blocking calls over here, so that's completely fine. It's going to be performant because so we can see that it skipped some names and it processed some names using the HTTP server. So it's going to be performant because virtual threads are fast to create, they are fast to switch between, and we can actually schedule a lot of blocking calls to run in the background, and this will not put a lot of strain on the operating system or on the platform threads that are created to actually run the whole thing. Okay, so that was the HTTP server demo, and I also would like to show how exceptions are handled, right? So I told you that the stack traces when using futures, for example, either in Java or in Scala, are not that useful, and here we are in a better situation. So here we have a flow, again an infinite flow, where we emit natural numbers. For each natural number we sleep for a second, and then at a random point in time we just throw a runtime exception. To make things a bit more interesting, we merge this flow with another one so that things will run concurrently in the background, right? So this flow will actually run in a background thread. So when we run this, you can see that we will get a couple of ticks, and then we get, after 3 seconds, an exception, right? And this exception has the full context, allowing you to pinpoint where the problem actually is. So you can see that the root exception is a channel closed exception. This comes from the fact that this flow was run in a background thread. So we have over here, we have a stack trace entry which points to the merge invocation, which actually started this thing in the background. And then as the cause, we have our exception, and you can see that we can also pinpoint where it happens. So we can actually reconstruct the whole tree of invocations, even if there are like some concurrent and threads running in the background. So we can actually reconstruct the whole thing. Okay, let's stop the HTTP server. We won't need it. The exceptions are done. Okay, so now let's look at some internals of how actually this works. And these internals, I think, are surprisingly simple. So the class flow, it just apart from exposing a number of operations allowing you to construct flows and to manipulate flows that are already constructed, it doesn't really have anything else. So a flow contains just a flow stage, and a flow stage has a single method run. So this method contains the logic that defines what should happen when this flow is run, right? Like run to list or run for each and so on. And as a single parameter, we obtain a way to emit elements from the flow. Emitting elements from the flow is a matter of just running a single apply method. And that's it. The built-in flow stage is actually quite simple if you try to read the code, you know, and if you think that's too simple, like what's the point? Like, I could do this at home, right? Then yes, the goal of Ox is to be very simple and to provide all of these simple things that you actually need to write direct style code for you so that you don't have to do it, right? Also, another important thing is how we signal completion and errors. Well, errors are very straightforward, which when there's an error, run will simply throw an exception, and if a flow ends, well, run will simply complete, and that's a completion signal. So of course, if you, for example, if you are starting some concurrent flows in the background, the run method of, for example, a merge stage might include running other flows to channels, and then once these complete, you can do, you know, some extra cleanup logic or something like that. But these are the internals of a flow. So finally, I would like to show how to integrate flow with other libraries. So, you know, I guess these methods and these utilities that I have shown you, they are useful, but of course the biggest value is when you can integrate a streaming library into some other tools and into some other systems that you're using. So Flow is a very young library, so we don't have many integrations that are available out of the box. So that's something that we want to work on, and we hope to get your feedback on what should we work on first. But just to get you a taste of what such integrations entail, let's look at a simple Redis example. So in our example, we will be using a Redis queue, so something similar, if you know Kafka, where you append values to a log and then you have a client which reads values from the log. So that is something very similar. So So far there's no aux and no flow here. We are just using the Redis Java API client Lattice. So what we are doing here is we are connecting to Redis. We are not doing any cleanup. That's of course in production don't do it, but in a demo I guess it's fine. So what we do is we add values to a test stream that we define over here, and we just send value 0, value 1, value 2, and we do it once every 1 second. So that's on the right side. Now on the read side, what we do is we once again connect to Redis, of course, and then in an infinite loop we read messages from a read group. So we create a read group over here so that our position in this stream is persisted across restarts. Yeah, so we create a group 1, consumer 1, reading from the test stream, the same stream that we have written to before, and then what we simply do is we do some processing. We fake some processing, so maybe we should actually switch those. So we fake some processing for 2 seconds, and then we acknowledge that this message has been processed, and we read the next message, and so on and so on. So you can see that this actually works. So we will start the writer in the background, right? So it sends some messages, and we can start the reader as well. So that's the writer, and you can see that the reader processes values slowly, so the writer is faster than the reader, so this works nicely. So now let's say that we would like to convert this stream of values that we obtain over here into an aux flow. So what would we need to do to obtain a flow which emits values that are read from this Redis stream? So that's actually once again quite simple. So what we can do is we can use the flow using emit constructor, and the using emit constructor gives us a way to emit values which we will use. So we surround this everything into a block, and yes, so this we'll simply run drain. Okay, so to get rid of the warning and to actually run the flow. So what we do here is we create a flow which might emit arbitrary values. So this emit object over here, it can be used to emit values. So we have to use it to actually emit values downstream. So this whole code that we have over here actually remains exactly the same. The only difference is that we, instead of printing over here, we will emit the key that we have obtained over here. Okay, so that's the key difference. So now once you call emit, it will actually call all the downstream consumers of that key in a blocking way. So if you know, if the subsequent stages of the flow are in some way blocking, this emit call will be blocking as well. So once this key is processed by the downstream flow, we can acknowledge that it has been actually processed, which doesn't have to be true in case of concurrent operations. So we can, you know, run this stream in the background, emitting all those values to a channel, and then reading from the channel in another thread. So you know, this actually might mean only that the value has been produced to an intermediate channel or a buffer, right? So this acknowledgement actually probably should be done a bit differently, but here once again it's fine. So now that we have a flow, what we can do is we can call let's say a tab on it, right? So we can print line the key that has been obtained, and then we can tap once again to sleep 2 seconds. So we can move this processing over here, right? But we need to ignore, so we can say that processing the key. Okay. So we do the processing over here, and then we simply run the flow discarding all the values. So we can see if it works once again. So we start the writing process, okay, and now we start the reading process as well. Yeah, so it started from value 7 because it picked up from the last moment we stopped processing the stream, but you can see that it's actually, you know, using the code that we have written. Once again, we are sleeping for 2 seconds. So that's it. So just to recap, if you want to create a custom flow, if you want to integrate flow into your toolchain, what you need to do usually is using the flow.using emit. So that's the most flexible way of defining flows. The emit instance that you get over here can be used to emit values downstream, and it might be a blocking call because it will only complete once this value is processed by whatever downstream consumers there are. One important note is that this emit value and emit is thread unsafe, so it should not be used on any background threads. It should not be usually captured in, you know, and stored. It might be captured. It should not be stored in any kind of values, lambdas, closures, and so on, so that it doesn't escape this scope over here, right? So if you do need to, if you want to run some things in the background and emit values that are somehow captured in the background, you should use channels to communicate between the background thread and the main thread that is actually running the flow, which will also run this code over here. Okay, so that's a Redis demo. Finally, I have a quick Kafka demo. So Kafka consumers and producers is one integration that is already available in Ox Flow. It provides code very similar in essence to the Redis integration that we have done. It's a bit more involved because Kafka is also slightly more complex to properly use, and there's a couple more features when it comes to, you know, producing and consuming streams. So what we can do over here, we have an example of a Kafka producer. So let's maybe start with that. So here once again we have a flow, a completely ordered flow, like no concurrency or anything, that just produces instances of a producer record that are that you might know from the Kafka Java client. So what we do with that flow is we run it with a specific drain, right? We want to run it and publish all these values that are emitted by this flow to a Kafka topic. So that's as simple as running kafka drain.run publish. And this actually contains the entire logic. So you can see that we are creating like a concurrency scope over here. We are managing exceptions. So this actually is something that involves concurrency because Kafka reports exceptions on a side channel. So we have to collect those exceptions in the background thread, and so on and so on. So that's the publishing side, and once again we have the consumer side, which is very similar in spirit to the Redis example that we have seen, although we are just using predefined components. So we can use a Kafka flow which emits values from a topic, right? So we had the Kafka publish drain, and here we have the Kafka flow which emits values that are read from a topic. So we can subscribe to a topic, and we obtain simply a flow of consumer messages, of a received message, and then we can, you know, map on it so that we have access to the offset of the message, and so on and so on. So we can, once again, we pretend to do some processing in the flow, and then we can run it. So here what we do is we read values from one topic. So we subscribe to one topic, we pretend to do some processing, and then we write values to another topic, committing offsets in the first topic once the write is done. So that's a fault-tolerant way of actually transforming data from one topic to another. And I think the plumbing required here is quite simple. We can use the full power of the Flow API that we have just seen. So we can just verify that it actually works. So we've got the Kafka producer, Yeah, so it's sending some messages, and we have the consumer, which we can run over here. Yeah, so it's connecting, yeah, and it's processing some messages in a slower way, right? So what we are doing here is we are duplicating the messages that come in, and yeah, we just sleep for 2 seconds. Okay, so that's Kafka, and that's about it when it comes to Flow. If you would like to find out, take a look at some more examples, we've got 2 examples in our projects. That I will put those links in the description of the video. So one of them is a WebSocket chat that is using Tapir. It's using aux concurrency scopes. It's using flows to define the logic of how to transform the incoming WebSocket messages to the outgoing WebSocket messages. We also have a ChatGPT proxy where the incremental responses are streamed to the client as they come in. So it's a simple proxy, but you might do some processing of either the queries that are sent to ChatGPT or the responses that are coming from it. And that's about it. It would be great if you could try out the project, if you could try out aux, and if you could start on GitHub. That will help us know that people are actually interested or not. So if you will have some suggestions as to what kind of integrations we should provide first, please let us know. And with that, I think we are done. So thank you and see you next time.